Hello, I'm Dr. Joshua Reichert, and this is a software tutorial for the OGS statistical analysis software entitled Practical Statistics for Social Research. This software is entirely web-based and it is proprietary. It was developed in-house here at OGS, and it's intended to make statistical analysis for sociological research as straightforward and streamlined as possible. It was especially designed for students who are completing a doctoral dissertation, and we included the most common statistical tests for the most common research designs. Throughout this tutorial, I'm going to walk you through how to use the software using the example data sets that are included within the interface. You're welcome to follow along and have this tutorial open on a separate monitor or in the background, and you can open up stats.ogs.edu to access the software. Software is free and open to anyone who wants to use it, including current students, alumni, faculty, and even the general public. Our hope is that by releasing this software to the public, that we can advance our standing among higher education institutions and achieve our vision of becoming the world's preeminent institution for sociological research from a Christian perspective. And we can do that by sharing a tool like this with the broader world. So let's start by looking at the interface. It's relatively simple. You'll see it's divided into major steps, and those steps are outlined in headings. So we can see step 1, input data and choose options. Step 2, run descriptives and assumptions. Step 3, run statistical procedures. And step 4, review results. Let's go back up to the top of the page and look at step 1. Step 1 is designed for data input, and most statistical tests require only 2 samples. These are usually dichotomous variables, that is, divided by 2. And most statistical tests make comparisons either between 2 groups with the same dependent variable, split on some independent variable, or 2 dependent variables that are tested for correlation. And we'll give you examples of each of those statistical tests as we move through this tutorial. You'll see that the 2 samples are represented by input boxes, and there are options for you to label those samples. By default, those are labeled as group 1 and group 2. You can easily copy and paste data from a spreadsheet like Microsoft Excel or a comma delimited text file like a CSV directly into these text boxes. And each row represents one observation in the sample. You'll notice that down below, there's an indicator of how many rows are present in the text box and which row you are currently on based on the cursor location. Let's start by loading an example data set, and that will help give some context to what you see here on the screen. So if you scroll down, there's a button that says Example Datasets. Click that, and you'll see a drop-down box. Let's select one of these examples, and we'll start with an independent t-test. This data set includes 1 dependent variable, and that's scores on an instrument called the Ethical Decision-Making Scale, EDMS. And those scores are ratio level data. You can see those are decimal values, 2 decimal places. And the 2 samples represent 2 dichotomous groups split on an independent variable. And in this case, the independent variable is religious participants versus non-religious participants. Now, for purposes of research, imagine that you administered an instrument, the ethical decision-making scale. And one of the demographic questions you asked was, do you identify as religious or non-religious? And whether a participant said yes or no to that question determines which group their data would fall into. And we now have two dichotomous groups split on an independent variable that we can compare. You'll notice that the independent samples checkbox is checked, and that's because these are two unequal groups. The people who are in the religious participants group are not the same people who are in the non-religious participants group. These groups are independent of one another. In fact, they're not even the same size. So this sample has 16 observations. This sample has 20 observations. And so independent samples should be checked in cases like that. In fact, let's take a moment to talk about research design. An independent samples t-test is an example of a quasi-experimental design. And a quasi-experimental design is an alternative to a traditional experimental design where you would have an observation and control group. In social research, we generally don't have control groups or placebo groups like you might have in pharmaceutical research or laboratory research. And the reason for that is it's very difficult to actually control human participants, especially when you're using something like a survey instrument. So instead, we use what's called a quasi-experimental design, quasi meaning almost experimental. And instead of splitting the groups on the basis of random assignment to a control group versus an experimental group, we instead split them on some arbitrary independent variable, in this case, religious versus non-religious. And that's why this is called a quasi-experimental design. And for this particular quasi-experimental design, we're using an independent samples t-test because, well, our samples are independent of one another. As we move through the demo, we will go over a dependent samples t-test as well. So now that we have data loaded into these two input boxes, we can actually get right to the data analysis. But if you're interested, you can actually edit these data. And if you were inputting them manually, you could just add additional rows here, or you could copy and paste directly into the box. Try to make sure the data are as clean as possible, eliminate any extra spaces or commas or things like that. The software will attempt to clean your data for you, but try to provide it the cleanest data as possible. So just numbers on each row. Now that we have the data loaded, we can now scroll down to step 2. And in any social research, we want to see both descriptive statistics and assumptions tests. Descriptive statistics give us a summary of these two samples. And there are some things we can infer about the descriptive statistics, but for the most part, they don't tell us anything about the actual tests that we intend to run, in this case, an independent samples t-test. But descriptives are an important part of the process. When we get to step 3 of actually running statistical procedures, what we will be doing is running inferential statistics that helps tell us something about a comparison between these two groups. But for now, we can simply run the descriptives. And to do that with this software, you can just hit the descriptives button. You'll get a nice explanation that tells you what each of the generated items represent, and it gives you a quick summary of what each of those values means. And if we scroll down, we'll actually see output in APA format with tables and, in some cases, developed paragraphs of textual output in addition to the numerical output. For descriptive statistics, we will receive, in this case, 2 summaries, one for each group, our religious participants and our non-religious participants. Under each of these headings, we have a table that shows a variety of descriptive measures: the sample size, the mean, the median, the mode. Those are measures of central tendency, as well as the standard deviation, the maximum value, the minimum value, and the variance between those values within the sample. It also generates a horizontal histogram, and most histograms are flipped 90 degrees, and you would look at these bars stacked vertically. In our case, the histogram is just rotated 90 degrees to the right, and the bars are represented horizontally. But as you can see in this sample, we have most of our values are in the range of 4 to 6 and 10 to 12. And then we have a variety of values in the range of 7 to 9 and 13 to 15. We also get a box and whisker plot that tells us about outliers and how the values within each sample are distributed. And we get a nice overview of the minimum, the maximum, the quartile ranges, and the median for the box and whisker plot. And the same thing is repeated for the second sample, our non-religious participants. All the same values are here, and the box and whisker plot is also generated. So for the most part, you can utilize what's generated by the software directly into your research study or dissertation. You will want to write out some descriptive paragraphs of these values to explain what the tables and the figures are displaying. Let's scroll back up to step 2 and now click on the Assumptions button. Assumptions are preliminary tests that tell us something about the nature of the sample that help us determine which statistical test is most appropriate for our study. Within social research, we have generally 2 categories of statistical tests: parametric and non-parametric statistical procedures. Parametric refers to the population. And if we have usually a large enough sample size and a normally distributed sample that looks like a bell curve on the histogram, then we can use what are called parametric procedures. And that simply means that they apply to the population parameter. That means we can generalize the results to the population, the target population. But if our samples do not meet certain assumptions tests, then we cannot apply or generalize the results to the population. And the results apply only to the samples themselves. Now, is one better than the other? Well, if you're aiming to generalize your results to the target population, yes, certainly you would want to aim for an adequate sample size and a normal distribution so that you can use parametric procedures. But for purposes of a dissertation or a small social research study, for maybe a case study or a very contained journal article, you would not need to use parametric procedures as long as you make it very clear that the results apply only to the sample and not to the entire population. So when we click Assumptions Tests, we get a variety of output, including a summary of skewness and kurtosis. And this tells us something about the shape of the histogram and the shape of the distribution. So in this case, it tells us that this sample had negative excess kurtosis. The distribution had lighter tails than a normal distribution. This indicates fewer extreme values, as fewer outliers than expected in a normal distribution. It also tells us that the distribution was skewed to the right. The right tail, larger values was longer or fatter than the left tail. This indicates that the bulk of the data were concentrated on the left side of the distribution. However, even though these slight excess skewness and kurtosis existed, the sample visually generally appears to be close to a normal distribution. Now, here's where the interpretation comes in. It's up to you as the researcher to interpret these assumption tests and determine whether or not a parametric procedure is appropriate or if you need to default to a non-parametric procedure. And skewness and kurtosis are just two data points among several that we'll look at here in the assumption tests. Now, the software also does some basic normality tests. These are actual statistical procedures to test whether or not the distribution is normally distributed. The first test that's done is the Kolmogorov-Smirnov statistic, and it will give you a value between 0 and 1, and generally a value closer to 0 suggests that it is indeed close to a normal distribution, and the software will tell you this in the output. So in our case, the KS statistic is 0.19, which is relatively close to 0. And the software also does a simplified version of the Shapiro-Wilk statistic. And that determines whether or not the expected quantiles match a normal distribution. And in this case, a value closer to 1 indicates that the sample follows a normal distribution. And again, it tells you that in the output. And it will run both of those tests for both of the samples, religious and non-religious participants. Now, the software will also run a test for equal variance, and there are several tests that can be run. In our case, we run Levine's F statistic and the F test, and we actually get a probability value, a p-value for Levine's test and a general F test. Now, what's interesting is even though these values, the two normality tests and the skewness and kurtosis, seem to indicate that possibly there was that the sample is close to a normal distribution, we have to look at these values as well, because at least for this second sample, the p-value in each case is not less than 0.05, which tells us that these might not quite have equal variances. So now you have a decision to make as the researcher of whether or not you should or should not use parametric procedures to analyze your data. So let's scroll back up and look at options under step 3. You'll notice that all of the statistical tests are organized under research designs. And we have the first category of tests organized under quasi-experimental or causal-comparative designs. We are looking at a quasi-experimental design with independent samples. We could look at a causal-comparative design, which generally uses dependent samples, and we'll do that in the next example, that a database that we load. But let's assume that we said, well, we think that based on the shape of the histogram, the skewness and kurtosis, the two normality tests, all things considered, we think that the data are normally distributed enough to justify a t-test. And a t-test in this case would indeed be the parametric option for statistical analysis. If we said, we're not sure that the sample size is large enough, we're not sure that the sample is normally distributed, then we could revert to a Mann-Whitney U procedure, which is the non-parametric alternative to a t-test. And so the software actually tells you that. Here are the parametric options, here are the non-parametric options. Let's start with the parametric option, assuming that we think we can go that direction. Again, all we have to do is click t-test, and the software will run the statistical procedure. In our case, we have two independent groups, and we have the means listed here of those two groups. We have degrees of freedom, the t-statistic, and a p-value. Now, the software will automatically generate hypotheses for you, and you'll probably need to tweak these to match exactly what you intend to measure. And this will be based off of what you inputted above under the sample labels and down here in the box labeled dependent variable label or labels. And here we put in the ethical decision-making scale for our dependent variable. So just to be very clear, the ethical decision-making scale score, EDMS, in fact, we could even put the word score there, is our dependent variable. And whether or not someone is religious or non-religious is our independent variable, the means by which we split the data into two groups. So we can scroll down, let's hit t-test again. And now you'll see that the software generated a null and an alternate hypothesis. No statistically significant difference exists in the mean scores of the ethical decision-making scale score between religious participants and non-religious participants. In fact, because the software automatically puts the term mean scores there, we could probably remove that from our dependent variable label and leave it the way it was and rerun our t-test. And now the hypotheses are a little more coherent. So this is our null hypothesis, and here's our alternate hypothesis. Now remember, in social research, the objective is not to prove a hypothesis. The objective is to see if we can sufficiently reject the null hypothesis within a particular scope of probability. And that's what the p-value represents. When we say that the p-value has to be less than 0.05, what we're really saying is that there is a 95%, the inverse of 0.05, a 95% probability that if we resampled the same population, we would get the same statistical results. So what we're looking for is a probability value of less than 0.05, meaning that we have 95% confidence that if we ran this study again, we would get the same or similar results within a particular statistical range. In this case, the p-value is 0.0005, which is much less than 0.05. And the software generates some narrative for you and then helps you interpret. So it says the p-value of 0.00050021 suggests a statistically significant difference between the group's means at a 0.05 alpha level. The null hypothesis was rejected. And the software also gives you the output of some post-hoc procedures. And for a t-test, you can apply what's called the Bonferroni correction. And what that does is if you have a lot of hypotheses that are just essentially trying to throw spaghetti at the wall to see what might stick, it's good practice to indicate that on the Bonferroni correction. And what it does is it actually keeps cutting the alpha value in half to make it a little more difficult to reject the null hypothesis with each additional hypothesis that you add to the study. And that can be adjusted at the top here under tools and options by indicating the number of tests that we intend to run. And it will actually adjust this alpha level automatically. We scroll back down. We also can measure Cohen's d, which is a measure of effect size. And if applicable, we can get a power statistic. Let's go back up here to the top of the application. And I do want to mention a couple of things because we've mentioned sample size, we've mentioned the alpha level. If you look under step 1, I showed you already what is listed here under tools and options. And some of these things are some tweaks that you can make to the statistical test depending on the nature of your own study. But if you go to sample size and power, we have included a sample size or power calculator for you, much like sample size or power calculators that exist elsewhere on the web. If you click calculate sample size, it will tell you that with a power of 0.8 and an effect size of 0.5, you should have at least 95 samples in your study in order to achieve that particular effect size and power level. As effect size decreases, the sample size is going to increase. So if we increase the effect size, notice now that the sample size decreases. And this is just another factor that you can use to determine whether or not your data are normally distributed and whether or not you can use parametric procedures. So I wanted to point that out to you so that you can see that that is a tool that's available to you. If you would like to experiment with a normal distribution, so you can see exactly what a normal distribution looks like. In fact, we'll just reload the page and click on Tools and Options. And now you'll see that there's an option that says Generate Normal Distributions. If you click on that, the software will randomly generate two groups with normally distributed samples. So if we click down to our descriptives, we now see our histogram looks almost like a perfect bell curve, a perfect normal distribution. And that gives you a sense of what a normal distribution should look like if, in fact, you choose to use parametric procedures. Again, that's not the only factor that determines whether or not a parametric procedure is appropriate, but it is one among many of the measures that you can take into consideration. Sample size is usually one of the most important. As you can see here, both of these groups have 300 observations in them, so these are quite large. And the larger the sample size, generally, the more likely it is that you'll end up seeing a normal distribution like this. So let's reload the page and go back to the example databases and load our independent t-test for the ethical decision-making scale once again. But this time, let's run a non-parametric procedure. The non-parametric alternative to the t-test is the Mann-Whitney U procedure. So we scroll down to step 3 and we click Mann-Whitney U. And now we get similar output to the t-test, except this time we get the results of the Mann-Whitney U procedures calculations. Notice that the p-value is pretty close. It's pretty similar to what the t-test computed. In fact, we get the same result, that the p-value suggests a statistically significant difference between the group's distributions at a 0.05 alpha level, and the null hypothesis can be rejected. Just note that the Mann-Whitney U procedure compares distributions rather than sample means. And so here's an example of using a non-parametric procedure. If you did use the Mann-Whitney U procedure for this study, you would simply put into the limitations section of your study or your dissertation that the results cannot be generalized beyond the sample itself. It cannot be generalized to the target population. And that's okay, because it's still valid research. In fact, it has even more credibility because you carefully delineated what the data can and cannot say based on examining all of the factors that we talked about concerning a normal distribution. Let's continue now and look at a dependent samples t-test or a dependent samples quasi-experimental design. If you scroll down again to the example databases, and from the dropdown, this time choose dependent t-tests achievement scores. Let's see how this is a little bit different. In this example, we have two equally sized groups. Each group has a sample size of 25. And notice that the independent samples checkbox is not selected. In this example, we have academic achievement scores, maybe on a standardized test. And we have a sample from the fall and a sample from the spring. This is what's known as a causal comparative design, and it usually compares before and after, pre-test, post-test, or 2 points in time on a single dependent variable. And so now, instead of splitting our groups on religious, non-religious, we're splitting our groups on fall and spring. But the big difference here is that our sample sizes are the same. And that's because each row represents a single student from the fall to the spring, from the fall to the spring, from the fall to the spring. And in this case, we want to know, was there a statistically significant difference in student academic achievement scores from the fall to the spring? Something that an educator would certainly want to know. Now we can scroll down. You could run your descriptives and your assumptions just like we did before. But this time we're going to run a dependent t-test. To do that, you just need to make sure that this independent samples checkbox is not checked. So let's make sure here it's not checked. And we'll scroll down and we can click the t-test button again. Notice the software automatically ran a dependent t-test for you. And we get a similar output. We get similar hypotheses. And it tells us that a two-tailed student's t-test was applied to dependent samples, assuming equal variances. I should point out that you can change those options under Tools and Options by selecting whether it's a two-tailed or one-tailed test and whether or not you want to assume equal variances in the samples. So let's scroll down. We get a very similar output with a null and alternate hypothesis. We get some narrative. And again, the software will tell us that the p-value of 0.010 suggests a statistically significant difference between the group's means at a 0.05 alpha level, and the null hypothesis was rejected. So this means that, yes, there was a statistically significant difference from fall to spring. Now, note that we're not asking whether or not the scores increased or decreased, which is something an educator would probably want to know. We're just asking if there was a statistically significant difference between the two. We can do some additional analysis to determine whether or not the scores increased or decreased, but if we wanted to make this a little more robust, we could force a one-tailed test to see not only if there was an increase or a decrease, but if there was a change in one specific direction. And again, you get your post-hoc procedures for the dependent samples t-test. Now, the non-parametric alternative to a dependent samples t-test is the Wilcoxon procedure. So we can scroll up to step 3 and just click Wilcoxon, and it will run. Now, Wilcoxon is non-parametric. So if we determined that the sample size wasn't large enough, that it wasn't normally distributed, that it didn't meet those assumptions tests, then we could use this as an alternative to a parametric dependent samples t-test. And the Wilcoxon procedure uses what are called ranked sums rather than comparing means. And the software will write that out for you in the hypotheses, and it will give you a little bit of a narrative for the findings. By the way, you can always click this little button at the bottom to take you back to the top, and you can click this button to copy the contents to your clipboard to paste it into Microsoft Word. It It's not always perfect, so you may need to do some tweaking once you paste it in, but by and large, it will save you a lot of time because everything is generally already formatted to APA format. So let's go back to the top. And now let's shift gears a little bit and try a different research design. We're going to move from t-tests, which are quasi-experimental and causal-comparative designs, to a correlational design. And a correlational design essentially means what it says. It's a co-relationship. How are two variables related to one another? The important thing to remember is that a correlational design must have two dependent variables at the ordinal, interval, or ratio scale or in order to complete the procedure. You cannot have categorical variables for a correlation. So if you're splitting the data on something like religious, non-religious, a binary variable like that, or if you have multiple categories, which we're going to look at when we do the ANOVA procedure, that is not a correlation. A correlation must have two continuous variables. And in this case, we have these two continuous variables in each of the samples. We have hours of weekly religious involvement in one sample and a score on an instrument called the Life Satisfaction Index. And what we want to know in this case is, does hours of weekly religious involvement correlate with someone's life satisfaction? Notice that the two groups are the same size. Both have 19 observations in them. Why? Because this is the first participant. This participant had 0.9 hours of religious involvement each week and a score of 6.74 on the survey instrument. This person had 3.4 hours of weekly religious involvement per week and a score of 8.26 on the instrument, and so on and so forth. So notice that these two scroll bars are in sync because each of these rows are attached to each other. Each of these rows represents a single participant. And what we want to know is, are these two continuous variables correlated? Do they correlate? Now, we can run all of the same descriptives and assumptions that we ran before on the data, so we can do that really quickly and take a look at the summary table and the histogram and the box and whisker plots. But what we're really interested in now are the statistical procedures for correlational designs. The parametric option is Pearson's correlation, and the non-parametric option is Spearman's rank or Kendall's tau b. Let's start with the parametric option. We'll click Pearson's correlation. Again, we get a very fast output generated by the software. We get a p-value, we get the correlation coefficients and the group means. The software and gives you a nice summary of the findings. In this case, 5 hypothesis. The software will also generate a scatter plot graph to show you where these data are plotted on an XY graph. So, for example, in this case, the x-axis might be hours of religious involvement, and the score on the life satisfaction index. And we plot each of those points on the graph, and then the software will try to determine a trend line through that scatter plot. Now you can see this does not look like a very clear linear correlation. If it did, all of these dots would be tightly plotted around that trend line, and they are not. So it does the best it can to try to estimate something here, but this is not a very good correlation, and you can see that visually. Let's scroll back up to step 3, and if we want to try a non-parametric alternative, we can use Spearman's rank correlation. So we click that, and we get very similar output, and we get the same scatter plot. And again, even though it's a little closer to 0.05 in Spearman's rank, the null hypothesis could still not be rejected. And we can try a third option, which is Kendall's tau b, another non-parametric correlational procedure. Click that. And this time it's even worse at 0.67. And in this case, no, it could not be rejected once again. So that's a very simple correlational design. You also have the option of doing what's called a linear regression. And a linear regression creates a function, a linear function, just like the line that we looked at, that becomes a predictor of particular values within your correlation. So if we have a really good model, if we have a good, strong correlation, then we could run a linear regression to actually predict some future outcome. So in our case, we could actually predict the number of hours of religious involvement if we knew somebody's life satisfaction index, or we could predict somebody's life satisfaction index score if we knew how many hours of religious involvement per week they were engaged in. So it's just algebra. You can plug in one of or two of those variables and solve for the other if you have a really good linear equation. So let's scroll back up to the top, and on our set, use perfect correlation. And this will give you an idea of what a perfect correlation actually looks like. So we chose that. It loaded these two variables, and notice they're just labeled X and Y, but we're going to see what and we can click Pearson's correlation, and notice that the p-value is 0. Why is the p-value? We are absolutely certain that this model is perfect. We have full confidence that if we run it again, we'll get the same results. Because look at that on this line, because those to one another. They are co-related in a perfect linear fashion. So if we go back to linear regression, now the linear regression model will actually generate a function. And if you remember from high school algebra, this is the format of y equals mx plus b, where we have a slope and a y-intercept. And so with this equation, we can now predict x based on y or y based on x with perfect accuracy in this case, because we have very artificial data, but it's used to illustrate the point that we can build a predictive model. So if you have a really good correlation, you can actually build out with a linear regression, you can build out a predictive model for your two variables. So just remember that a correlation means what it says. It is a co-relationship between two continuous variables. Let's now proceed to do a little bit more complicated statistical work. And we'll click on example data sets again. And this time we're going to choose the ANOVA procedure. And ANOVA stands for Analysis of Variance. And it's used when we have several different categories and one dependent variable. So in our first example, we had religious and non-religious. But what happens if we have more than two groups? Well, this is where the ANOVA procedure comes into play. In this example, we have in the first box a list of groups, and these groups are denominations. So we have Methodist, Church of God in Christ, Catholic, Methodist, Baptist, Pentecostal, Presbyterian, so on and so forth. And on the right-hand sample, we have scores from the social trust scale. Notice these are ratio values from that score, from that scale. And notice here that this checkbox is checked. Sample one specifies groups, because here on the left-hand side, these are our groups and these are our values. So notice this, each row scrolls in sync. And the reason for that is because this participant was Methodist and this was their social trust scale score. This person was Kojic and this is their social trust scale score. This person was Kojic. This was their social trust scale score. This person was Lutheran. This is their social trust scale score, and so on and so forth. And it's important that both samples are exactly the same size, because these two values are linked or represent the same participant. So let's scroll down. We can run our descriptives and assumptions just like we have before. One thing to note, when you run descriptives with an ANOVA study, it's going to look a little bit different, just because we have categories now instead of just two samples. But you can run those. And now we can scroll down to step 3 and notice that the ANOVA procedure is listed under quasi-experimental designs. And the reason for that is because it is a quasi-experimental design. But instead of having just two groups to compare, like a t-test, it has multiple groups that we can compare. So let's just click that button for ANOVA, and here's our output. It gives you some nice narrative, and notice that it gives us the means and the sample size for each group. We only had one participant who was non-denominational. We had 6 who were Kojic, and so on and so forth. And there are the mean scores for the social trust scale per group. Then we get the actual output of the ANOVA statistics, including an F statistic and a p-value. And we also get 2 post-hoc procedures, the omega squared and the LSD procedure. Notice that we also get what are called pairwise comparisons for any significant differences that were found. So these tell us that there was a difference between Lutherans and Methodists, Lutherans and Catholics, Lutherans and Baptists, so on and so forth, in either categorical direction. And then we get some additional between and within group effects for the ANOVA procedure. And again, you'll need to flesh this out in narrative in your own study. But we have the sum of the square, the mean square, and degrees of freedom within and between the groups. It will also generate the null and alternate hypothesis for you. And again, write out the findings, including an analysis of the F statistic and the omega squared statistic, to indicate whether or not there was a small, medium, or large effect size. And that helps to give some context and interpretation to the data. So in summary, an ANOVA procedure, analysis of variance, is used when you have multiple categories for one dependent variable. And in this example, we're of course looking at denominational groups applied to one instrument, survey instrument score. And we're looking to compare that score between those various groups. We can now move on to an extension of the ANOVA procedure, which is called the two-way ANOVA. So we'll click on our example data sets and then choose two-way ANOVA with a moderating variable. Now, this is the most sophisticated of the statistical procedures that our software supports. But in this example, we might have participants in 2 categories, let's say, that are male or female by gender of clergy. And then we might also want to look at church location as a moderating variable. And we want to know, what role does the interaction between clergy, gender, and church location, either urban or suburban, what interaction effect does that have on a congregational vitality score, let's say? So that might be something that a church consultant comes in and applies to a congregation, of how vital that congregation is. And we want to know, is there an interaction effect between clergy, gender, and church location? Notice a couple things. We do have category labels here for the dependent or moderating variable. And this checkbox is shown, show moderating variable will actually give you this third input area that shows up between the two that you normally see on the input screen under step 1. And again, we have sample 1 specifies groups checked. Notice again, 15 and 15, these groups are equal in size. So we have 2 moderating categorical variables, that's nominal variables, and 1 ratio variable that's our dependent variable, congregational vitality score. If we scroll down, we can click on two-way ANOVA, and it will generate the hypotheses for us. Now, there are main effects and interaction effects for a two-way ANOVA. The main effects are congregational vitality score based on clergy gender, congregational vitality score based on church location, urban or suburban. But what's really interesting about the two-way ANOVA is the interaction effect. And so that third hypothesis is formatted a little bit differently. And it says no interaction effect exists between clergy gender and church location on mean congregational vitality score. So now we're asking these two other moderating variables, or the moderating variable of church location on clergy gender, is there an interaction effect between those two things on our dependent variable? And it gives you some output, including p-values for the main effects, 2 main effects, clergy gender, church location, and the interaction effect. And as you can see here, for both the main effect on clergy gender and the interaction effect is less than 0.05, but for the main effect of church location, it is not. And so that's up to you to interpret those values accordingly. So that's an example of the two-way ANOVA procedure. Next, we'll demonstrate the chi-squared procedure. And chi-squared is used here at OGS, typically in the Action Research Project for the DSL degree program, but it can be used for hypotheses in a PhD dissertation as well. A chi-squared procedure is inherently non-parametric in nature, meaning that it's not robust enough to use it to make any kind of generalizations to the target population. So as long as you have clear limitations of what it can and cannot do, it's perfectly acceptable. The chi-squared procedure is a form of a quasi-experimental design, and it's used when you have all nominal or categorical variables. And most often, those come in the forms of frequency counts or rates. And it's important to identify when this is appropriate, because if you have variables that have rates or frequency counts, those are categorical in nature. So how many green hats, blue hats, white hats, red hats, or how many tall, medium, or short people were involved, or how many people came on Monday, Tuesday, or Wednesday to a particular event. Those are all categorical or nominal levels of measurement. Let's click on example databases. And then from the dropdown, we're going to choose chi-squared before and after training. And this is a pretty typical example. So in this case, we have what's called a chi-squared matrix. And this is for the chi-squared test of independence. Chi-squared looks at association between nominal or categorical variables. As you can see, this is very simple data. On our left-hand sample, we have before the training workshop, and on the right-hand sample, we have after the training workshops. Much like a causal comparative design, this is saying what was a particular score before, or particular nominal categorical count before and after some event, oftentimes a workshop like this, a training. It acts almost as an intervention, so to speak. And then under the dependent variables, you notice we have 2 separated by a comma, active volunteers and inactive volunteers. And if you can visualize, that would look like a matrix with 4 quadrants. We would have before, after, active, inactive in those 4 quadrants. And as you can see, we have just 4 simple numbers, and these are counts. These are just frequency counts. So we had 5 active volunteers before the training workshop and 11 active volunteers after the training workshop. We had 12 inactive volunteers before the training workshop and 6 inactive volunteers after the training workshop. And that's it. A chi-squared matrix is that simple. So we can scroll down, and with one click on chi-squared, we get the output. And it gives us a visualization of that chi-squared matrix. And these are essentially our 4 quadrants here in these 2 columns. It gives us a little bit of narrative and then the output. And there are 2 p-values here, and they're computed differently, but we get a typical p-value and then a sometimes more precise measure or a different measure, Fisher's exact p-value, which just makes the analysis a little more robust. It generates a null and alternate hypothesis and then gives us a summary of the findings. And as you can see, because p is less than 0.05, we can actually reject the null hypothesis. It's pretty amazing that a chi-squared procedure can give us this depth of statistical analysis with such simple nominal or categorical numbers. But it is a well-recognized statistical procedure, and it is appropriate when you have frequency counts or rates or any other nominal variable that you need to compare against each other. And it's very appropriate as long as it actually reflects your instrument and your variable, and your hypotheses are framed accordingly. So these are often used, chi-squared procedures are often used in the action research project because the action research project is centered around some kind of intervention. We want to measure before and after, and we don't typically administer psychometric instruments. In the DSL program, we're just looking at frequency counts. So how many attended before, how many attended after, so on and so forth. So that statistical procedure is available to you when it is appropriate. The final procedure that I want to demonstrate in this software training is Cronbach's alpha. And most students at OGS will not be using this, but for alumni and faculty and anyone else who's using our software, this may be useful to you. Cronbach's alpha is used to assess the reliability of a researcher-created scale, typically a Likert style instrument. Let's click on example databases and we'll load Cronbach's alpha. In this case, on the left-hand sample, we have a repeating list of 1, 2, 3 items. So think of those as items on an instrument or questions 1, 2, and 3. And then if we piloted this instrument to a group of pilot participants, these are the ratings on those Likert scales, 5, 3, 1, 2, 2, 5. And again, those are synced together because this is participant 1, this is participant 2, this is participant 3, and those are the 3 items on the instrument, and these are the corresponding values. So just for purposes of demonstration, we have these labeled as the construct and the responses. So the construct could be anything that you're trying to develop, a religiosity scale, some sort of sociological measure of attitudes, knowledge, or behavior. And for the dependent variable, we're just calling it a Likert scale for purposes of demonstration. So scroll down, and under step 2, you can click on Cronbach's alpha to run that procedure. And now we get a table with items, how many items were in each sample, the mean values, and then it gives you a very simple output and tells you how well the reliability was rated for that scale. And as you can see, it actually gives a letter grade on Cronbach's alpha, and this was an F, less than 0.06, considered unacceptable reliability. And that's most likely because this is a very small sample size. So really only 5 participants in this pilot test at 3 items each. So this is available to you if you want to utilize it to test a new psychometric instrument that you might be working on, or sociological scale. And you could continue to run your pilot test and maybe even eliminate particular items based on how the reliability scores come out until you get something that's acceptable. It meets acceptable reliability criteria. To conclude, I'll just show a couple more features here. You click on example databases and choose from the list. There's an option that says split group data. This can be very useful if you have data arranged in columns in a spreadsheet. So in this case, I have gender in one column, and I have male, female, male, female, male, female alternating. And then these are the scores, let's say, associated with those genders. But I want to get all of my male scores into one column and all my female scores into another column so that I can run a t-test. Well, the software will do that for you. So if you paste this in from Excel, click on Tools and Options, there's something here that says Split by Groups. If you click on that, it will automatically move those into the correct groups for you and set up the 2 independent variables accordingly. And we can scroll down and run the t-test. And there it is. There's the output. I hope you enjoyed this demo. I welcome you to use our software. You can just visit stats.ogs.edu, and you can also access it from our homepage under the research tab. And if you have any questions, please feel free to reach out to us, and we will be here to help and support you as you utilize this software for social research. Thank you.